In this video, we are going to look at a weak acid, strong base, titration. So, since we're dealing with a weak acid and a strong base, I know that the pH at the equivalence point is basic. So that is going to give me an idea of a way to guide my calculations. So to do this problem, let's look at an example. We have 25 milliliters of acetic acid, and that is a 0.1 molar solution, is titrated with a 0.2 molar KOH solution. Calculate the pH after the following additions of KOH. So the first one we're going to do is 0 milliliters. So this is going to be before the titration has happened. And then we're going to do 10 milliliters. $12.5 milliliters, and 15 milliliters. Now, before I start this problem, I like to look at what I'm dealing with. So I have acetic acid, which I know is a weak acid, and I have KOH, which I know is a strong base. So when you're doing these types of problems, the very first thing you want to do is calculate how much of each substance you have in solution. So we want to calculate the millimoles of the acid and base present. Now I use millimoles. You don't have to use millimoles. You can use moles. That's just fine. I find it easier to deal with millimoles because it gives us numbers like 1.5 or 3 instead of 0.0015 or 0.003. So when you calculate the millimoles of acid and base present, what you are doing is you need to identify where you are on the titration curve. So there's 4 different regions on a titration curve. You have your initial pH. So that is before you've added any of your titrant in there. The second area is known as the buffer region. And this is going to be before the equivalence point. Now, in this buffer region, you're going to have your weak acid or weak base and its conjugate acid and conjugate base. So what that means is you have a buffer. So that's why it's known as the buffer region. The third point is going to be at the equivalence point. This is when you have equal parts acid and base for a titration where it is a 1-to-1 mole ratio. And then finally, we have the fourth area, which is beyond the equivalence point. So for this example that we're doing here, my initial point is going to be no KOH. And then at the second area, we're going to have more acid than the base. Now, at the equivalence point, then my acid is going to equal my KOH. All right, and when we say that, we mean the millimoles of our acid is equal to the millimoles of our base. And beyond the equivalence point, this is where we're going to have more KOH. Now, the second thing you need to do is calculate the concentrations needed to get the pH. Generally, this is going to either be calculate the concentration of hydronium ion or calculate the concentration of hydroxide. Now, let's look and see what this titration curve is going to look like. So I can establish my curve. I'm going to have milliliters of base on my x-axis, and then I'm going to have pH on my y-axis. Now, since this is a weak acid, strong base titration, I'm going to start out at an acidic pH. And so before I've added any of my base, I'm going to have an acidic pH because I have only acid present. And then as I start adding base, the pH is going to go up, but it's not going to go up linearly. It's going to go up very gradually until all of a sudden it will shoot up and then it will even out. Now, where it is going up gradually, this region right here, this is the buffer region. And in that buffer region, you're going to have both acetic acid and acetate present. Now, the buffer region is the only place where you can use the Henderson-Hasselbalch equation. I find that when we're doing titration curves, people want to plug that in everywhere, but you can only do it you can only use that equation in the buffer region. So, let's start this problem. Part A was with 0 milliliters of KOH. So this is going to be my initial pH. At this point, I'm going to have 0 milliliters of KOH times my 0.2 molar KOH. So the reason I'm using millimoles here is because I don't have to change my milliliters into liters. So that's one less conversion. Notice my liters cancel out and I am left with millimoles. So this will give me 0 millimoles of KOH. Now, do you have to do that calculation? No. I am just simply showing you how we don't have any millimoles of KOH present. Now, I don't need to calculate the millimoles of my acid because I already know where I am on my titration curve, right? If I don't have any base present, then I know I have to be right here. This is my initial pH, so that is where I have to be on my titration curve. One of the biggest mistakes I see at this point is when you are calculating the pH. So now I know I need to calculate the pH of a weak acid. So if we recall, we can use the concentration of hydronium ion is equal to the square root of Ka times the initial concentration of my acid. So for this problem, I need to get the Ka of acetic acid, and I need the initial concentration of my acetic acid. Now, again, this is concentration here. I cannot plug millimoles in here. And this is a common mistake I see is people will calculate the millimoles of the acid present and then plug that into the equation. But you cannot use millimoles, we have to have concentration. So again, at this point, we only have acid in solution because we haven't added any base. So I am going to have to go out and look up the Ka value for acetic acid in my book. When I do that, I get Ka is equal to 1.8 times 10 to the negative 5. So the concentration of hydronium ion is going to be equal to the square root of 1.8 times 10 to the negative 5. And I'm going to multiply that by the initial concentration of my acid, which is 0.1. If we plug that into our calculators, I get 1.35 times 10 to the negative 3. And that is good to 2 sig figs based off our Ka value. Now, I have the concentration of my hydronium ion, so I can get the negative log of that to calculate my pH. And my pH is going to be equal to 2.87. So if we go back and look at our titration curve, here at point A, the pH is 2.87. Now, does that pH make sense? Yes, it does, because I only have acid in solution, so I should get an acidic pH. All right, let's look at part B. This is with the addition of 10 milliliters of KOH. So the first thing I'm going to do is calculate how much of my acid and base I have in solution. So I have 25 milliliters of my acid. I got that from the problem right here. We have 25 milliliters of 0.1 molar acetic acid. So I can multiply that by my concentration, and that gives me 2.5 millimoles of my acetic acid. Now I can do the same thing with my KOH. And that gives me 2 millimoles of my KOH. So there's 2 reactions going on. First, we're going to have the neutralization reaction, and then I'm also going to have the reaction of my weak acid. So at this point, the millimoles of my acid are greater than the millimoles of my base. So that tells me I am before the equivalence point on my titration curve, and I know that before the equivalence point is going to be the buffer region for a weak acid, strong base titration. So I can set up my neutralization reaction. I'm going to have acetic acid reacting with hydroxide. Remember, potassium is a spectator ion. We don't really care about it. This is a neutralization reaction. It does not exist in equilibrium. So we'll have that yield water and acetate. So when I start out, I'm going to have 2.5 millimoles of acetic acid, 2 millimoles of my hydroxide, and I don't have any of my acetate. So in this case, the hydroxide is the limiting reactant, so that is going to be completely consumed, and it is going to be converted into acetate. So once this neutralization reaction is complete, I'm going to have 0.5 millimoles of acetic acid. I'm not going to have any hydroxide left, and I'm going to have 2 millimoles of my acetate. Notice that all I have in solution are my weak acid and conjugate base. So all that is present in solution is the weak acid and conjugate base. Well, what does that make? That is a buffer. So at this point, I know how much of my weak acid and conjugate base I have in solution, so I can plug it into my Henderson-Hasselbalch equation. So pH is going to be equal to pKa plus the log of the concentration of my conjugate base, which in this case is my acetate, over the concentration of my acetic acid. So I'm going to have to calculate my pKa. Remember, pKa is equal to the negative log of your Ka. So I can plug that in here and I get 4.74. So my pH is going to be equal to 4.74 plus the log of 2 over 0.5. Now I know some of you might be thinking, why are you plugging millimoles in when you need concentration? Well, mathematically, if I have something on the top and the bottom and I divide both of those numbers by the exact same number, realize concentration is molarity over liters. So they have the same volume in our solution. I would add my 25 milliliters and 10 milliliters to get 35 milliliters. And to get that, I would divide both of these numbers by 35, so you would get the exact same ratio. Now this only works if you have millimoles on top, millimoles on the bottom, or moles on top, moles on the bottom, and you're dividing by the same volume. So now I can plug this into my calculator and I get a pH value of 5.34. Now, does this pH make sense? We are before the equivalence point, so yes, this pH does make sense. I have more acid than base. Now, in a strong acid, weak base titration, you have to realize that you could have a place where your pH could get slightly basic because at the equivalence point, the pH will be basic. But this pH does make sense. Our initial pH was 2.87. I added base, my pH went up. All right, let's look at the third point, which is 12.50 milliliters of KOH. Now, when you're doing these types of problems, the amount of your acid isn't changing because you start off with 25 milliliters and you don't add any more acid. So I still have my 2.50 millimoles of acid present in my solution. Now I need to see how much base I have. So I can take that 12.5 milliliters and multiply it by my concentration. And that gives me 2.5 millimoles of base. So at this point, the millimoles of base and millimoles of acid are equal to each other. So that tells me that we are at the equivalence point. Now, if this is the case, then this also has to equal the millimoles of my conjugate base. So let's first look at the neutralization reaction. So with my neutralization reaction, I'm still going to set it up the same. We have acetic acid plus hydroxide, and that is going to yield water plus acetate. So here we have equal amounts of reactants. So that means that they will both be completely consumed. So I won't have any acid, I won't have any base, and all I have present is my conjugate base. So we don't have any acid at all. So we cannot use the Henderson-Hasselbalch equation. We only have conjugate base present. So the concentration of my conjugate base is going to be 2.50 millimoles over my total volume. Now my total volume is going to be the 12.5 milliliters plus the 25 milliliters of base. So that will give me 12.5 milliliters of KOH plus the 25 milliliters of acid. I shouldn't have said base there. So I'll have a total volume of 37.5 milliliters. Now, when you're doing this, notice that the millis cancel out and you're left with liters, or you're left with units of moles per liter. Now, this conjugate base is going to act as a base in water. So I can have my acetate in water. It's going to exist in equilibrium to form hydroxide plus acetic acid. Now, since this is a base, it's going to have a Kb. And since this is the opposite process of the acetic acid dissociating in water, our Kb is going to be equal to Kw over Ka. So in this case, it's going to be equal to 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So just like we saw before, we have the equation hydroxide is equal to the square root of Kb times the initial concentration of my conjugate base. So when I get my Kb, which I calculate to be 5.56 times 10 to the negative 5, I can plug that in right here. And then I can multiply it by my initial concentration, which we already established was going to be 2.5 millimoles over 37.5 milliliters. Now, what you need to realize is, in this case, since we are using the concentration of hydroxide, then this will give us a way to calculate the POH. So I can take the square root of all of this, and that will give me 6.09 times 10 to the negative 6 molar. Now I can use these values to calculate the POH. POH, if you recall, is the negative log of the concentration of hydroxide. And that is going to give me 5.22. Now, in order to get the pH, I'm just going to subtract my POH from 14. So pH is going to be equal to 14 minus 5.22, which is equal to 8.78. Now, does this pH level make sense? I have a weak acid and a strong base. So at the equivalence point, I should have a basic pH. 8.78 is a basic pH. So yes, this does make sense. All right, let's look at the final point on our titration curve. So that was point D, and we were at 15 milliliters of our KOH. So again, the first thing I want to do is calculate how much of my acid and base I have in solution. I did not add any more acid, so I still have 2.5 millimoles of my acid, and now I have 15 milliliters of my base. and I can multiply that by the concentration of my base to get 3 millimoles of my base. So at this point in the titration curve, I have the millimoles of my base is greater than the millimoles of my acid. So we are beyond the equivalence point. And what that means is we have only strong base in solution. So this is very, very important. There is no Kb or Ka because it is a strong base. So in order to do this, I need to figure out how much of my base I have left over. So I'm going to set up my neutralization reaction. We're going to have acetic acid plus hydroxide yields water plus acetate. And we're going to have 2.5 millimoles of our acid, 3 millimoles of our base, and in this case, our acid is going to be the limiting reactant and is going to be completely consumed. So we won't have any acid and we'll have 5 millimoles of base. Now, will we have some conjugate base in solution? Yes, we will. However, the basicity is going to be coming from that hydroxide. So that's how we are going to calculate the pH. So I can get the concentration of my hydroxide by taking the 0.5 millimoles of the base that is left over after it has been consumed by the acid, and I can divide that by my total volume. I have 15 milliliters of my KOH plus 25 milliliters of the acetic acid, which will give me 40 milliliters. Now again, my millis cancel, and I'm going to be left with units of moles per liter, which is a unit of concentration molarity. So the concentration of my hydroxide is 0.0125 molar. Now, as soon as you have the concentration of your hydroxide, you can calculate the pOH. We just have to negative log it. And that will give me 1.9. Now, a lot of times people will stop here and say this is equal to the pH, but that doesn't make sense because we are beyond the equivalence point. There's only base in solution, so our pH should be basic. So at this point, I need to subtract that from 14. So I'll get 14 minus 1.90, which gives me 12.10 for the pH at point D. And that pH makes sense because it is a basic pH.